On the wall today, I've got a Solari Udine Clock, a flip clock, a classic piece of Italian technology that was probably installed in a railway station, and it was definitely installed in Germany because it has a Deutsche Telekom label on it. This clock needs a 48 volt bipolar pulse to make it work, and I don't have one of those because Deutsche Telekom doesn't offer a service here, so I need to produce a 48 volt driver for this clock. If you want to see how it works, see my other video, the link is below. If I'm going to design a driver for this clock, I need to know how to drive it. So I'm going to measure the current and the duration of the pulse. When the motor armature moves, it generates back EMF, and that has a direct influence over the current drawn by the clock. So we can actually see in the current flow what the armature is doing. So we're going to explore that in this video. The test setup consists of a 48 volt power supply, my digital storage scope, a 100 ohm resistor to measure the current, a switch to change the polarity, and of course the clock. When I send a pulse to the clock and it advances by 1 minute, this is the measure of the current going through the clock motor. But when I don't change the polarity and send a pulse to the clock so it doesn't advance 1 minute, it doesn't move, I get this flow of current through the clock motor, which is kind of interesting. In the next clip, you're going to see a split screen with the inside of the clock on the left, with the armature of the clock motor highlighted with a lime green circle. And on the right hand side, you'll see the digital storage scope, and that will trace the current going through the clock motor synchronized to the motion of the clock motor armature. The clip is in slow motion, and as a result there's a horrible amount of flicker on the digital storage scope, but it is what it is, and you'll still be able to make out the current flow displayed. The first sound you hear is the power button. It takes a while, but the motor armature starts to rotate clockwise. It only ever rotates clockwise. It builds up enough speed to generate enough back EMF to almost bring the current to zero. Then it changes directions and briefly rotates counterclockwise, where it generates EMF in conjunction with the power supply, so the current rapidly increases until it stabilizes. When comparing the current measured when the motor armature moves and when it's stationary, you can see that measuring the current flow tells a lot about how the clock is actually working. From this experiment, I now know that I need to provide a 48 volt pulse of at least 200 millisecond duration to properly drive the clock. But I have the option of measuring the current to check that the clock is mechanically working properly. The other input this clock required was 240 volts AC to drive a fluorescent tube that illuminated the clock face. I've removed that. I'm going to fit an LED strip that requires a constant current source because this is the most efficient. And to do that, I need to provide two 100 milliamp current sources, each providing at least 25 volts. Now that I've characterized the inputs that I need to make this clock fully functional, the next stage is to go through and figure out how I'm going to do it. There's a whole lot of options that I have available. I expect I'll be making a few more videos on this clock. Thanks for watching.